So I want to talk to you about our efforts to analyze this humongous ocean simulation and what we had to do in terms of various software packages to try and make that work. So before I start quickly, then who am I? I'm an oceanographer as of just over a year ago, working with Ryan Abernathy in the Pangeo crowd. Previously, I was a plasma physicist, so I went from plasma turbulence to ocean turbulence. I'm also an X-ray core dev, and this is my first SciPy, and I'm excited to be here. So what I'm going to talk to you about, firstly, I'm going to motivate the science question that we have. I won't go into great detail, but it'll provide a little bit of background. Then going to talk about how big the scale challenge that we're trying to address here is, how big the simulation that we're trying to analyze is. Then we're going to talk about how we try to refactor the libraries we use to compute on this data in order to scale better with Dask. And as particularly, I'm going to go into a bit more detail about this one library called XGCM and how we rewrote that around this concept of a grid U-func, which I'll explain in a minute. And then when we actually applied it, we ended up down this rabbit hole of scheduling changes to the Dask scheduler, which I think a lot of you will find interesting. So the science question we have, we imagine you have you have ocean velocity data across the surface, and you can compute the vorticity, the swirliness, and you can compute the strain, the stretchiness of that flow. And one of our co-workers, Drew Valwada, showed that by looking at correlations between these two quantities on a two-dimensional histogram, so a joint probability distribution function, which is what you're looking at in the bottom right, you can learn a lot of interesting things about the turbulence. So we want to compute the vorticity from the flow field, the strain from the flow field, and then bin them together on a histogram. So that means that our calculation looks like we start with gridded velocity data, which is on many faces because the simulation output that we're using has to take the sphere of the globe and split it up into these faces. From those, we need to compute the vorticity and strain from initial just like U and V velocities. And then from those, we need to bin them into a histogram and time average them. Okay, fine. But the problem is the scale. This is a snapshot from just a tiny part of this humongous simulation that we're using. We have this huge data set called LLC 4320, which is it's a global model similar to what Julius was talking about in his talk earlier on XMIP. Using a code called MIT-GCM. We didn't run this simulation. This simulation was run on a massive NASA supercomputer using 20,000 cores. We simply want to analyze the data that was saved. The grid spacing goes down to 1/48 of a degree, so there's thousands of grid points like around the circumference of the Earth, and it outputs an hourly time resolution. We have it stored in Pangeo Cloud Storage, so we can access it that way. But a single variable, so just, for example, the temperature of the water at the sea surface across the whole globe, just that one variable is enough to take nearly 9 terabytes of data, stored in like 100,000 ZAR chunks. We've got it in ZAR on cloud storage. And that's just the sea surface. So if we want to do this for the depth, because the simulation also resolves like down to the bottom of the ocean, then that would be truly a petabyte scale problem, which we do want to do at some point. But if we can't do it for the surface, we definitely can't do it for the full problem. So if you like an X-ray data set, if you have an X-ray data set and you're just looking at a single variable, for example, the velocity in the X direction, U here, this is what it looks like. And to give you an idea of how big this is, here's a little animation that Julius cooked up last night. And the top there is the bottom of South Africa, to give you an idea of how big this is. And you can see all the fine-grained turbulent structures that are here. And we have this for the entire globe, and this is just zoomed into one tiny bit of it. So this gives you an idea of how big this is. And this is the salinity we're looking at here, the salt concentration in the ocean. So, sorry. There we go. The second problem we have, on top of the scale, is that technically our grid data is staggered. And if you've ever done a fluid like dynamics simulation, you might know what I'm talking about here. But essentially it means that the certain variables, for example, the temperature and the velocities, are not precisely co-located on the grid. They're actually, technically, they're separated by like half a grid cell. And in a lot of cases, this doesn't matter. But if you're trying to do certain types of analysis, this can cause you to accumulate errors which you don't want to accumulate. And if you want to do if you want to replicate, for example, the finite difference operators that the full simulation used correctly, you need to take this into account. So with that second problem in mind, we have this XGCM package that our group developed. And XGCM is built to handle staggered variables. So essentially, it's difficult to handle these kind of variables within X-Array's data model alone. So you kind of have to extend X-Array's data model to add additional information about the positions on the exact grid positions on which data lies. And what matters is their relative positions. So, for example, the temperature might lie on the center of a grid cell, while the velocity might lie on the left-hand side of a grid cell. And then we store this information for all our different axes. So in our case, like latitude, longitude, time, in a grid object, which has a simple representation like this. And this is what the XGCM package does. The problem is that XGCM in its original implementation was very inefficient from a scaling point of view. So you could encode, XGCM provides you with finite volume operations like differencing and interpolation, which you can do along particular axes. But because of the way that it handles boundary conditions and padding on the edges of these arrays, then our custom reduction code would lead to an explosion of Dask tasks, especially if you chained operators one after another. So, for example, if I want to calculate something like vorticity by chaining a couple of like differencing operators, then this is just two differencing operators chained, and you don't need to know much about Dask as a parallel computing framework to see that this is a complicated graph that is probably not going to execute very efficiently. So a better idea was to rewrite the library in terms of this thing we're calling a grid ufunc. So the idea, it's motivated by analogy to a NumPy ufunc, in that it's the sort of the kernel of the operation that you want to perform, except that you also include information about the grid positions of the data before and after the operation. So if you have a differencing operation, it might expect data that lies on the left-hand side of the grid cell and return data that lies on the center of the grid cell. And this concept is language agnostic. Like, you could describe any function that acts on like staggered grids in this way. It's not specifically like a Python idea. And then you would have different, what we call signatures for different types of functions, depending on whether you're going like forward interpolation, backward interpolation, the order of the operator that you're applying, and so on. Our implementation for a very simple case looks like this. We import a decorator from XGCM. We decorate the function with the signature that explains what's going to happen to the input variable and what the resulting output where the resulting output variable is going to lie. But the function itself, the ufunc here, is a NumPy level function. So by wrapping it, then we are actually promoting it to something which accepts and consumes X-array objects, as well as checking the grid positions of the data that we're feeding it as well. And the whole point of this is to help avoid mistakes in user code, essentially. So the decorator itself has some other neat features. So being able to just decorate any custom function is quite useful, because a lot of the use case for this kind of thing is you have some weird like finite difference operator in some climate model that's written in like Fortran somewhere, and you want to replicate it in Python in your user code when you're analyzing the same variables, the output variables. And this way you can just write the function in sort of NumPy-like indexing, looping syntax, apply the decorator on the top, and then you should be able to immediately use that. So that's an example of a user-specific algorithm. Another thing we did is we allowed you to skip the signature, instead use annotated type hints. So I'm going to talk you through this code example here, but I'm going to go from bottom to top. Because in this particular case, imagine we're calculating like divergence of like normal like 2D vector quantity. We know that we've got to return two derivatives added together for that. The actual computation of the derivatives in NumPy land would look something like this. And then we tell it that the u variable coming in and the v variable coming in, we tell it that they lie on particular grid positions. So this is the left-hand position on the x-axis and the center position on the y-axis. And this is a type hint. You can import this from Python type hinting. So this is the type hint, and then you annotate the type hint with this extra arbitrary information. And the decorator sees this and reads it instead of having to pass a signature argument. And then you have the same thing for the return value. And then also padding is handled by, so padding and boundary conditions is handled by these additional arguments at the top, which essentially make up for the fact that our particular finite differencing operator here is going to trim off elements at the end of the array. Another nice thing about the decorator syntax is that you could chain it with other decorators. For example, like a number JIT decorator, you could insert here and then you'd get the benefit of the speed as well as all these other XGCM benefits. So we have this horrible graph before, and we rewrote XGCM from the ground up, basically, like all the internals, to instead rewrite all operations to pipe these ufuncs through xarray apply ufunc, which goes through dask apply gufunc, which means that we eventually end up with much, much simpler dask graphs. You can see this is much closer to a tree-like graph that will be executed from bottom to top. I think this one is for a mean or something. And this, because we can do this, we can decorate any function that we like to define, we no longer have the problem of chaining multiple operations leading to an explosion of tasks, because instead we can just define the full like vorticity or strain operator that we want in one go, decorate that, and the graph will be this simple. And just note for future, and I'm going to come back to this, this is a very nice graph, but it's not actually quite a tree because it has these, this is to do with the padding, these little loops in here, and that will be important later for when we actually try to evaluate this. So this was a big project to refactor it. We changed basically the internals of every single function in this package whilst people were using it, which meant that test coverage was crucial, and we have, if anything, too many tests. But we were able to do that with minimal destruction, basically, and it just emphasized the importance of like taking tests seriously. So that is what we need to do to compute the vorticity and the strain, but remember we've got to compute the histogram afterwards, so we've got to bin our two quantities, our vorticity and strain. And we have another package for that called xhistogram, and it does a lot more than just like a NumPy histogram function, because it can leave some dimensions unflattened, so you can compute the histogram along just a couple of dimensions. You can compute multi-dimensional histograms. You don't have to compute 1 or 2D. You can compute an ND histogram. This is a 2D histogram here. And it works with X-ray objects, and it needs to be scalable with Dask. But our original implementation didn't scale well enough for this problem. So with a little bit of help, some key suggestion from Gabe Joseph of Coiled, then he pointed out that histograms have this fundamental property that they're cumulative. So you're counting the number of values that occur in a certain bin, and you can do that for part of the array on one process, and then another part of the array on another process, and then by summing those counts, that's still like the valid result. So you can see in this graph, this says bin count, and it's bin count for like 2 chunks, and then it's going to be summed and then summed again. So it means that an arbitrarily large histogram can still be represented as what Dask calls a blockwise reduction, but it really means like a tree. And that scales really nicely. Dask is really good at these kind of graphs. So we rewrote our analysis to have like what should be really neat Dask graphs for these 2 libraries, and then we tried to run it at large scale. And despite them being theoretically reasonable, like, did it work? Did it work as well as we hoped? Unfortunately not, but for interesting reasons. And what would actually happen is that we would unexpectedly start to run out of memory and spill to disk. And I expect that quite a few of you who use Dask regularly, especially for like geoscience problems, might have seen the dreaded orange and gray before. But it basically means that like too much data has been loaded into memory and your processor is starting to spill to disk, and it will just grind to a halt and never really get there if this happens. So trying to work out what went wrong here, we distilled XGCM, our vorticity calculation, into a minimal fail case and showed the Dask people. And it turned out that there were multiple issues with the distributed scheduling algorithm, which would only occur in certain cases and at certain large scales. And both of those problems happen to be things which you're likely to, I can go into some of these in a bit more detail, but both of these problems are likely to occur for like geoscience, like array-based workloads, and less likely to occur for sort of like data frame kind of style workloads. So in particular, this first one is quite easy to understand, this root task over production. And it's essentially, if you imagine an embarrassingly parallel graph, just a series of individual tasks, and each of which basically needs to open a chunk of data, operate on it, and then save it back out or reduce it or somehow release the data, then each parallel task chain will do data opening and then data releasing. And if it's embarrassingly parallel, then in theory, your parallel execution engine should be able to get through this in a streaming-like fashion. It should understand that it should open, compute, release before it opens more. Unfortunately, if your graph is complicated enough in a subtle way, while still being technically embarrassingly parallel, you can get to this situation where it actually tries to be helpful by running extra tasks, but all those extra tasks correspond to opening more data, and you end up with this race condition where it opens more and more and more data, eventually overloading your memory if the scale of your problem is bigger than like the total amount of RAM that your cluster has. And this has been seen for like quite a while. It's just quite hard to reproduce exactly like what you need to do in order to get this problem to occur. But it just so happened that our test case was complicated enough to cause the problem, but simple enough to like understand what was going on. And this is a known problem. Like I got this image from a Dask blog post from like about a year ago. But what was great is that when we pointed this out and showed these problems, then people from the Dask developers, and in particular Gabe, who works for Coiled, he was helping me work out exactly what was going on and prototype some changes to the scheduler. And the performance difference after making these changes was insane. So this is a graph of the total memory used by our vorticity calculation over time before the change that he made to the scheduler and after the change he made to the scheduler. So you can see that not only has it gone down by like an order of magnitude, it's also become bounded, like it's not randomly spiking, and the computation finishes in about half the time. So it's better in every single way. And you compare these blue memory, like blue is good, orange and gray is bad, if you remember the previous plot, which is great. And this is exciting because lots of people might find that once these changes end up in main, that their geoscience workloads just run better as a result of fixing these issues. But they're not quite ready for use yet, is my understanding. So we, in the meantime, tried to look at some other ways to execute our calculation. One way I tried was with X-ray map blocks, and so basically I rewrote the calculation to parallelize in a different way, just parallelizing over time slices, and not as complicated as before, but also not as general. But that happened to suffer similar scheduling issues. We then tried something similar again, which using Dask delayed. So you basically artificially create a task which opens a chunk of data and then immediately saves it back out. So Dask just sees a single task that does both opening and saving, and then you create an embarrassingly parallel graph like that, which I'll talk about a little bit more on the next slide. But it also raises the question of whether we could have done this with other execution frameworks, which we did briefly look at. So other options might include X-ray beam, which there's a prototype for, and also this thing called cubed, which you might be interested in, which there's also a prototype for. But we didn't actually get around to using either of these yet. But we did manage to get it to run with the Dask delayed approach. So here now our graph just looks like this. So each task involves opening data, loading it in, computing it, and saving it back out to ZAR for that one chunk. And then we just do it for all our like 117,000 chunks. We ran this yesterday, and thanks to Brian and Julius and UV for helping out with that. And ran it on 400 Dask workers on Google Cloud platform, and it completed about 2.5 hours, cost us about $100-ish maybe. And this is what it looked like while it was running, and it ran really nicely. And you can see a graph over time of how much that cost us to do that calculation. So that was fun. And that means that we have some results as of last night to show you. Like, we did manage to do the calculation that we wanted to do. So in this case, the way we did it meant that we have histograms over time for many, about 400 different small regions all over the world. So if I pick one region arbitrarily, and this one just happens to be in the Antarctic circumpolar current, the strong current around Antarctica in the Southern Ocean, then we can plot the variation in this histogram between seasons, and the physical interpretation of this is to do with small-scale fronts in the turbulence having a seasonal variation, being stronger in winter and spring than summer and autumn, which has to do with stronger like vertical exchange within the water in that particular region of the planet. But we can now do this analysis all over the place, and obviously with that much data, there's going to be a lot to learn. So takeaways. We had a specific science problem at large scale that we wanted to solve. In order to try and do it, we rewrote two libraries, XGCM and XHistogram, to scale better with Dask. And in doing so, we came up with what we think is like a generally useful concept of a grid U-func in XGCM. But this did expose some Dask problems, which are now in the process of being improved upon by the Dask developers. And here's some of the libraries that we use if you want to go and have a look. And as a final note, then, if you found any of this interesting, then I'm looking for like next big project in a little while. So please reach out. But thank you.
Alrighty, at this time we'll take some questions. So if you haven't gone ahead already, go ahead and join the track questions, room 204. So the first question is, can you expand on working with scientists when you were doing the refactoring?
Well, in the sense that the XGCM maintainers, which is mostly me and Julius, we know that there are a number of geoscientists who use and download XGCM on a regular basis, and if we update and break something, then like someone's going to raise an issue and complain about it, which did happen a couple of times. But considering the size of the changes that we made, and we only got like 2 or 3 issues on relatively minor things raised, I think we did a reasonably good job of not disrupting those scientists' workflow too much. And the change version of this library has been out for like a few months at this point. So, yeah.
Quick follow-up.
Sorry, I have a question to ask you. I mean, because I thought that's awesome. And did you do anything special? Like, did you make announcements? How exactly did you stop the library breaking, or was it just you had good test coverage?
We had good test coverage, not total, like some of the bugs did sneak through, but we did have very good test coverage. We basically rewrote the new code path within the code base before actually deploying it on anything new, so that we could test it on all of these weird test cases. And then only as a last step did we actually like reroute the old functions through it. So many bugs were found before it actually touched like existing code. So there was this kind of like new and dangerous feature for a little while before everything else got routed through.
I encourage you to write a blog post or something on that, because we're in the process of changing a major data model in one of our packages, and we'd be really interested to hear, like, with your experience. I imagine lots of people would as well. Sorry.
Great. Cool.
All right, so next question. How much Dask work did you need to do yourself to help the improvements to the scheduler? I know the Dask team themselves are often busy.
Not a lot, really. I mean, so what happened? Basically, we tried to run it. It didn't work as expected. I presented the calculation pretty much as was on the Dask issue tracker, and there was some interest. And then simplifying it further, there was more interest, and then eventually ended up speaking to Gabe directly, and then we started going back and forth about how to like simplify the computation. And what was really useful is that Coiled gave me a bunch of free credits, so I was able to run on their platform, which was useful because if you've ever tried to like change the version of the distributed scheduler, that's like tricky. And so that allowed us to basically prototype it together. And then once we had like the minimum fail case, it was basically just like, okay, DAS developers, you go and like do your stuff. Yeah, which I think is kind of how it should be, really.
So is there a timeline then for some of the improved DAS scheduler functionality, or is that released yet? Or
I don't think it's released yet. You might want to look at, I can point you to the issues and read about it, but my understanding it scale of like weeks or a couple of months if it goes as planned is my understanding.
Awesome. Any other questions from the room? Yeah.
Yeah, that was a fantastic talk. Two questions. One, would you be able to provide some insight on how the distributed scheduler changes help to alleviate the out-of-memory issue with loading data in parallel, if you have like any insight on that? And then secondly, did you try using Ray? That's another like distributed computing system from Anyscale technology that is like quite similar to Dask.
Ray was mentioned briefly, but we didn't get around to actually trying it. I could try and explain exactly what the change to the scheduler was, but I think I'd probably get it wrong. So instead, I'd rather just point you towards like the issue where there's like detailed explanations of exactly what is being changed. And I think it's still like up in the air exactly like how it's being changed.
Okay, cool. Thank you.
Got a couple more questions.
Yeah. This is kind of obvious, and apologies if it sounds silly, but did you ever ask NASA to provide vorticity?
No.
Okay.
But I mean, that kind of isn't really the point of the exercise, right? Like the point of the exercise is we have some arbitrary computation that we want to do, like any analysis, and maybe we want some slightly different vorticity like next week or something. We need the ability to do that at this massive scale because that's what like analyzing the cutting edge science requires now. And it wouldn't really be feasible to like go back and forth and try and ask the original like people who ran the simulation to provide all of these things. And some of the things that we want won't exist. So
Okay.
does that make sense?
Yeah. I guess I don't know what Pangeo does. Is it providing people a product, or is it about doing computation? I don't know.
Well, in this case, it's a community and an ecosystem of software packages where the end goal is to allow geoscience scientists to scale up their analysis. And this is just an example of us pushing that to the largest scale that we could.
Thank you.
So I'll just make a comment if I can. In response to that question that was just asked, it's a very reasonable question, but it's really, when you're talking about petabyte-scale simulations, you really want to, like the main constraint is how much data can be stored. Right? Like it's a huge burden for NASA to own these like 10 petabytes of data. And like outputting more diagnostics when they can be derived from what's already been output is basically a non-starter. It's much cheaper and more effective to compute things that you can derive from those core state variables. And every simulation will have a certain core state variables and then other things that can be derived from those. And so that's a big part of what like post-processing of simulations is all about. I wanted to make another comment about, someone mentioned like the DAS developers can be busy or something like that. And I just want to mention some context about how we've been trying to operate. Since the beginning of Pangeo, we've had consulting contracts with companies who employ key maintainers of these projects. In particular with like distributed computing, something like Dask, it's a highly specialized thing. And it's like we don't have a lot of oceanographers who understand like the internal guts of like the Dask scheduler. And rather than trying to acquire that expertise ourselves internally, we found it's been very effective to partner with organizations, usually outside of academia, like Anaconda, QuantSight, Coiled, people who really do have that expertise, and have them on call to help us. And that helps them. Their business is trying to make money, and it's usually a lot more cost effective for us than trying to, like, say, hire a postdoc and spin up a postdoc with that skill. So I just mentioned this to the room because I think this is an approach we, as like scientists in academia, should be really trying to pursue more. It's been very effective here. We'd never be able to like figure out how to fix the DAS scheduler ourselves. We didn't have that level of engagement from the core DAS maintainers, but now that we have, there's a huge broad benefit that can be derived from that collaboration.
Great point. Do we have any other questions? If not, thank you so much, Tom. Let's put our hands together one more time.